All right, so last part of the week, we're going to look at sections 10.1 and 10.2, which focus on systems of equations. First of all, what does that mean when you're dealing with a system? What's different about a system versus just, say, an equation? Yeah?
You're running multiple variables?
Yeah, we have multiple variables, right? At least two. So it consists of two or more equations with two or more variables. Now, the problems that I give you, the number of variables will match the number of equations. So if there's going to be three variables, you're going to have three equations. But that doesn't always have to happen. You can have more or less of one or the other. And when that happens, you have what's either called an overdetermined or underdetermined system. Right? Here's an underdetermined system. Technically, I've given you one equation, and I've given you two letters. When there's more letters than equations, usually there's an infinite amount of answers. Right? So if I said, what's the answer to this equation? I mean, you can pick anything you want for x, and then just write down what you get for y. Okay? Now, if I take out one of the letters and do something like that, and say, well, what's the answer now? There's not an infinite number. That's one equation, one variable. There's only one answer. Okay? And then kind of the opposite of that, if you had something like, let's say y equals, I don't know, 3x, y equals 2x, that's doable. You can solve that. If you think about it graphically, it's just two lines and it's where they cross. Two equations, two variables. If you throw a third equation in, well, now you have an overdetermined system. If you think about it graphically, you're drawing three lines and you're finding where they all cross. Now, you might get lucky and they could all cross in the same spot. And in this case, they would. They all cross at the origin. But if I did that, now I've got two lines that do cross at the origin, and I got another line that has a y-intercept of 2. These three lines aren't going to cross in the same spot. I have more equations than I do variables, so it's possible you get a no solution, like in that case. All right, so our first example, we're just going to set up the system. We're not going to solve it. We'll come back to it, but I just want to set it up. Now, most of the equations that we use when we set something up, it's probably going to have two or three variables. Okay? In real life, when you're setting something up, like let's say you're trying to write a program to model the weather. Okay? I wouldn't even know where to start with something like that. But there's probably thousands of variables, from past data to current conditions like air temperature and humidity and wind and maybe the angle of the sun, and there's all kinds of variables. But we're not really going to get into anything that has that many variables. It's just like two or three. So pretty straightforward problem. They want you to find the length and width of a rectangle. And they tell you a couple facts. The perimeter is 100, and the area is 300. So all we're going to do is set up a system. So I'm looking for two equations, and I'm looking for two letters in each equation. Now, sometimes you have to just figure out your equations from scratch. When you're doing a geometry problem involving areas and perimeters or volumes, you don't really have to start from scratch. As long as you know the formulas for the shape you're dealing with, you can use that as a starting point. So we're dealing with a rectangle. What's the formula for the area of a rectangle? Yep. Area equals length times width. So we don't really have to think about what kind of equation we should use. Use the one for the area, and then we'll fill in after. How about perimeter of a rectangle? What's the formula for that? Chris?
2L plus 2W.
2L plus 2W. Okay, so now just fill in whatever we know, and we'll go from there. Let's start with the area equation. Tori, if I fill in what I know, as much as you can, what will this equation look like? 300 equals L times W. Now, if that's all you knew, I'd say there's an infinite amount of answers. It's an underdetermined system. One equation, two variables. Pick any two numbers and multiply to give you 300. But you can't pick any two numbers because they give you a fact about the perimeter. Emily, how much is the perimeter? 100. So when you pick L and W such that they multiply to give you 300, they also have to take double each one and add to 100. Okay. And that's it. So we've set up our two equations. We'll come back and solve them in a little bit. Questions on setting those up? Okay, so now when we solve a system, we're going to talk about a few different ways you can do it. What's one method you can use to solve systems of equations?
Substitution.
Yep, substitution. That's a good method for this one. We can use substitution. What's another method? Might not work as well on this one, but it does work pretty well sometimes. Yeah.
Elimination.
Yep, elimination. Elimination is good when you've got columns of things that line up, like x plus y equals 7 and negative 8x plus 6y equals 4. You line them up under each other. Elimination. What's another method for solving systems besides elimination and substitution? I talked about it right at the beginning of the lesson. So usually it's a slower way of, it takes a little longer to do it this way. And it's not always as precise without technology. Yeah?
Graphing.
Graphing. Yep. So you can always graph, with at least with 2 letters, it's okay to graph because it's still 2D. When you get into 3 letters, it gets harder. Now you're graphing 3D. Not easy to do by hand. And then a fourth method you can use is it's a matrix. Okay? And a matrix is based off of elimination. Right? But it's a little different way to think about it. Right? So here we're going to look at substitution and elimination. Okay, I don't mind substitution when there's really just 2 variables, but when you start getting into like 3 or 4 variables, substitution gets kind of annoying. But we'll practice a little bit. So remember, with substitution, first thing you have to do is pick an equation, and then within that equation, pick a variable. So for the problem we just did, we would have 4 choices. We could pick equation 1 or 2. The one for the area or the perimeter, and then from there you could solve either for L or W. But pick an equation, pick a variable to solve for. Okay. Once you get that variable by itself, plug it into the other equation. Once you do that and you simplify, at this step, step 2, you should now know one of your answers. Whichever one, it depends. Like if we do the length and the width, we might get the length first, we might get the width first. Do it either way. And now, once you know one of the answers for the length and the width, plug it back into one of the original equations to get the other answer. Now, if you've done everything right up to step 2, and you take your answer from step 2, it doesn't matter which original equation you plug back into. They both should give you the same answer. If you plug your answer in from step 2 into each equation and got different answers, then you did something wrong. Okay, so just real quick outline of substitution. Okay, same thing you've been doing with that since Algebra 1. All right, so let's solve this problem. I can make these L's and W's Doesn't really matter, but okay, so step 1 is to pick one of these equations. We'll call this one equation 1, equation 2, and solve it for a variable. You can't really make a wrong choice. You can make a more difficult choice, but you can't really make a wrong choice. So which equation should we pick to try to get a letter by itself? Rob? What about me?
Number 2.
All right, number 2. And which letter do you want to get by itself in number 2?
L.
L. Okay, how would you get L by itself?
Divide 300 by W.
Yep, divide 300 by W. I think that's the quickest way to get a letter by itself. If you pick equation 1, you get a little more work to do. All right. So Nate said we're going to get L by itself. We're going to divide each side by W. Okay. So now I've got a formula for L, and once I know W, all I got to do is plug it into this formula, and it'll give me L. Now, what do I do with the 300 divided by W? Yep. Put it in the other equation for L. Okay, so we're going to have 600 over W when I multiply the 2 out. You can think of it as 2 over 1 if you want. So multiply that out. 600 over W plus 2W equals 100. Okay, what would I do next there? Yes, Robin?
Like terms.
Okay, if I had any like terms, I would combine them. I don't see any like terms there. Remember, if you wanted to think of this W as having an exponent, this would have an exponent of 1. Since this W is in the bottom, it's like having an exponent of -1. So we don't have any like terms. Yep.
Multiply 100 by W.
Okay, I like the idea of multiplying by W, and where do you have to do it?
Where the 100 is.
Okay, anywhere else?
Would be on like both sides.
Both sides, right? If you're going to multiply by something, you got to change everything, which is fine. But you got to do it here, here, and here. Okay, so these are gone. That gives me 600 plus, what's going to be the other term I have after the 600? Chris?
3W.
No, that would be 2W plus W. Rob?
2W squared.
2W squared equals 100W. Now, it's not written exactly in the order we normally would write this kind of equation, but what kind of equation do I have to solve now? A what?
Not linear anymore.
Yeah, not linear. It's a degree higher than that.
Quadratic.
It's quadratic. So that's a quadratic equation. So now we either use the quadratic formula, factor it, right? See what happens. So if we're going to factor or use quadratic formula, we always got to get it equal to what first? Got to get it equal to 0. So I'm going to keep the 2W squared on the left, move the 100W over with it, plus 600 equals 0. Okay. Now there is one thing we could do here, especially if we're going to attempt to factor it. Anyone see something we could do? Yeah?
Factor out 2.
Yeah, we can factor out a 2 or divide everything by 2. All right, so now let's see if we can factor that. We're trying to think of 2 numbers that would multiply to give us 300 and add to give you 50 or negative 50. Anybody think of 2 numbers that multiply to give you 300? Add to give you negative 50. And we could start making a, a chart. 1 and 300, 2 and 150, 3 and 100. Does 4 go into 300? No, I don't think so. How about 5? 5 times how much is 300? 60. All right, that's not going to work. How about 6? Does 6 go into 300? Yeah, how many times does 6 go into 300? 50. All right, 7? No, I don't think so. 8? I don't think so. 9? 300, whoa. 300 divided by 9, no. 10, yep. 10 and 30. So, I don't know, we can keep going, but I'm not sure we're going to find anything. 11, no. 12 into 300, yep. 12 and 25. We're getting to the point where these two numbers are going to cross pretty soon. And once they cross, then we can stop. 13, probably not. 14, I doubt it. 15, let's see, 15, no, I don't think, yeah, 15 and 20. So 15 and 20. And 16, no, 17, no, that's not going to work. 18, let's see, I don't think that's going to work. 19, that's not going to work. So that's all we got. Is there any combination there of numbers that add to 50? No. So we probably should have just done quadratic formula. Okay. So if I'm going to do quadratic formula, what's A going to be? Not 2. I mean, you could do it with 2, but we're doing it with smaller numbers. We made it 1. Yeah. B? Negative 50. And C? 300. So we got 50 plus or minus the square root of B squared, which is 2500, minus 4AC, all over 2A. All right, so let's see what we get. 50 plus or minus, what's 4 times 300? 1200. And what's 2500 minus 1200? 1300. And that's the reason right there why we weren't able to find an answer, because the square root of 1300 is not a nice number. Okay, so let's see what we get. We get 50 plus the square root of 1300 and divide that by 2. So we get about 43.03. And what are we solving for? W. But we also have another answer, right? We've got 50 minus the square root of 1300 divided by 2. So we get 2 answers for the width. We get either 43.03 or 6.97. So let's call that width 1 and width 2. So that means I'm going to have L1 and L2. Okay. How would I get L1 now that I know W1?
Plug W1 back into your original equation.
Yeah, just plug it back. I would just plug it right into this one. Just take 300 divided by W, and there's your answer for L. So watch what happens. 300 divided by 43.03. 6.97. And what do you think I'm going to get for L2? 43.03. Or maybe 0.4 because of rounding, but. So when they ask you to find the dimensions of the length and the width, there really are 2 answers, but what's the difference between the 2 answers? Like if you were to actually draw those two rectangles out? What would be the difference? Yeah.
It would be the same dimensions, but basically either much longer, skinnier, or tall, skinnier.
Yeah. It's the same rectangle either this way or that way. You're just looking at it from two different, either laying on the long side or is it standing up on the short side. But technically there are two different answers, even though it's just the same rectangle rotating. That's how you're viewing it. Okay, so not every problem will involve quadratic formula. That just happened to come up in the kind of problem they gave us.
And when you got, with 1 with 2 by plugging, you got the original first two answers by the quadratic formula, right?
Yep.
And then you just plugged it into the, which equation?
I used a modified version of equation 2. I used a rearranged version of it because that would be the fastest way to get L. Yep. You could have used equation 1, it just would have been a little bit more work. Right, so let's take a real quick look at that. If we were going to solve it with substitution, which I'm not saying that may or may not be the best way to do this one, but if you're going to solve it with substitution, which equation would you focus on and which letter would you get by itself in that equation?
The first one, get y by itself.
First one, get y by itself. So y equals 5 minus 2x. If you were doing this in the context of graphing, you'd probably be thinking y equals mx plus b, and I didn't write it that way. But we're not graphing it, so that's fine. Right. And now what would I do with the 5 minus 2x? Yep. Okay.
Substitute it for the y.
Yep, substitute it in for the y, and we get 3x plus, and I'm going to double everything as I do it. Remember, it's a distributive property to the y. So 10 minus 4x, that's 2y, equals 2. Okay, and now just solve for x. So we're going to get, what, negative x on the left, and 2 minus 10, negative 8 on the right. So x is 8. Plug x back in, and we can get y. Okay, so when you plug x back in, what would you get for y? Yeah. Negative 11. And there's your two answers. Now, if I were to graph these two lines, okay, I'd have to get y by itself. I'm going to do it on the calculator and graph them. Where would they cross? Yeah.
When you cross it out, when
They would cross at 8 and get 1. So we basically just found where those two lines would intersect. Okay. And because they're lines, there aren't multiple answers like in the last problem. If you draw two lines, they can only cross in one spot. Unless they're the same line, then they cross everywhere. But that's kind of a special case. Okay. Any question on that? So, elimination. So elimination would have been good for the last problem. Okay, it's when you've got columns, right? And you line up all your like terms in different columns. And the goal is to get the coefficients in one column to be opposites. Like positive 3x in the top row, negative 3x in the bottom row. Or positive 10x, negative 10x. So I always get them to be opposites. I mean, technically you could do the same, like 3x and 3x, and then think of it as subtraction. but I always like to think of it as addition. So I get one to be a positive number and the other one to be the same but the negative. And remember, when we were dealing with linear combinations, that means you might have to multiply a row by a constant to make that happen. Okay? And we kind of did something like that early on when we factored out a 2. It's kind of, or divided everything by 2, or forget exactly what we did. But that's the idea. Whatever you do to one term, you've got to do to every term at the same time. So let's try, yeah, that's what I just told you. You might have to multiply one equation by a constant or both. It depends on the problem. But the goal is to try to find the least common multiple, right? You don't want to multiply by a number bigger than you really need to. But. All right, so let's look at this equation. Substitution, probably not an ideal way to do it because neither equation is going to be that great to solve for a letter. It's not that hard, but there's a better way to do it. So first thing we want to do is pick a column. And then from there, we want to try to make the numbers in front of that the coefficients opposites. So do we want to make the x's opposites or the y's? Which one? Yeah. X's. Okay, so we're going to try to make the x's opposites. So I have a 2 and I have a -3. You've got to find a number they both have in common, a multiple. What's a number, what's the least common multiple of 2 and 3? How much? 6. Yep. So the goal is going to be to make one equation have a 6 in front of the x, make the other equation have a -6. Don't worry about what's going to happen to the y's or anything else. Just try to get a 6 and a -6, and then we'll go from there.
I was told when I was in 6th grade that if you have trouble finding the least common multiple, that you should just multiply the two numbers together and you'll get it. Is that true?
Yeah, you could always multiply. It won't always give you the least common multiple, but it will give you a multiple. Yeah. For example, if I had 3x and a bunch of stuff and 6x and a bunch of stuff, you could make these 18. But you could also just make them both 6. So multiplying the two together will always give you a multiple, but it might not be the least common multiple. In both these cases, 15 is the smallest number for the y's, and 6 is the smallest one for the x's. Okay, so what would we multiply the top equation by? Yeah, I would multiply it by 3. So I'm just going to kind of put like a distributive property. And what could I multiply the bottom equation by? Yeah, 2. Okay, so if I multiply the top equation by 3, how about, Jacob, what would that give me when I do that out?
The 6x plus 9y is equal to 15.
And how about, Ashley, the bottom equation?
-6x plus 10 equals 42.
Like that?
Oh, 10y.
10y. Okay. Now, once you have numbers that are opposites, just add the columns. 6x, -6x. Gone. 9y, 10y. Gives me 19y. Let's see, 42 and 15 gives me 57. So you're not always going to get a nice answer, but we do here. What does y come out to? 3. Now do the same thing that we always do. Plug it back in. This time you don't have an equation that's really going to be quicker than another. Just plug it back in for y, and we'll figure out x. All right, so let's, maybe I do the top one because there's no negatives. Numbers are a little smaller. So 2x plus 3y. Y is 3. So 2x plus 9 equals 5. Let's see. So we're going to get 2x equals -4. So x is -2. Okay, so any question on using elimination? If a problem doesn't say which method to use, you can use any method you want. So, kind of, I think I already mentioned this a little bit, but when you're solving equations with two variables, they are lines, right? Assuming the variables aren't squared or anything like that. Okay, we're just talking about a problem that's set up like the one we just did. No variables in the denominator, like in the area problem. No squared, nothing like that. That's why it says linear. Okay, so when you're dealing with linear equations, three things that can happen. One solution. You draw your two lines, they cross in one spot. No solution. What kind of lines would have no solution? Yep. Parallel. So basically, if I gave you something like y equals 3x plus 6, y equals 3x minus 8. If you graph those, they're just going to have different y-intercepts. They're parallel. No solution. An infinite solution. How can that happen? Yep. Same line. Might not look like the same line on paper when you get it, but if I gave you like y equals 3x plus 6 and 2y equals 6x plus 12, it's the same equation. All I did was take everything in the top equation and double it to get the bottom one. Right? So they're the same thing. So infinite solutions, same line. Questions on the special cases? Okay. Right, this one let's solve it quick because I think it is going to be a special case. Does anyone see what you could multiply just the top by? And if you do that, tell me which letters would be opposites. Okay.
Multiply the top by 3 and it would be 6x and -6x.
Yeah, so if we do the top by 3, actually not only are the x's going to be opposites, but I think both the x's and the y's are going to be opposites. So you're going to get 6x minus 9y equals 5, negative 6x plus 9y equals 10. Gone, gone. What's on the left side?
And 15 and 0.
0. And on the right side? 15.
Isn't
Yeah.
you have to times it by
I didn't times that by 5. 3 times 5 is 15. Still get the problem right here, but you should remember to multiply everything. So you get 0 equals 25. Whenever all your letters are gone, you're done. You just have to figure out what that means.
no solution.
That means no solution. This is false. Don't write false. But that's what that means. You ended up with a false statement, which means no solution. If you end up with a true statement, like 7 equals 7, then it would be all infinite amount of solutions, or you could write all real numbers. So that's a special case. So if you were to graph these are parallel lines. So if you put them in y equals mx plus b, you'd see they've got the same slope. Any questions on them? Okay. That's another special case, which probably comes out to a true statement, but I'm going to skip over it. Let's look at 3 variables. So, with 3 variables, you got kind of a lot going on. You get a lot of choices about what you do first. So the idea, though, is you break it down. You're going to focus on 2 out of the 3 of the equations, and just try to eliminate a variable in those 2. So you do that first. Then, once you've eliminated one of the variables out of those 2, you're going to have 2 equations and 2 variables. You're going to try to eliminate one more. And then you're going to be down to 1 equation with 1 variable. Then once you can find one of the variables, then you kind of go backwards. Right? You plug that back in, and you start getting your other answers. Okay? So we'll go through it, and what I'll do is I go through it, I'll label my equations like, I'll give them numbers, like equation 4, 5, 6. Now, the way I'm showing you how to solve a 3x3 system, it's not the most efficient way. Okay, using a matrix is more efficient. This ends up being kind of a lot of writing, but the advantage is it doesn't require me to teach you anything new. All you're going to do is use elimination a bunch of times. Elimination and then use substitution at the end to get all your answers. Okay, so here's our system. Okay, I have 2 of these, but we'll probably just end up doing one of them. We'll see. And usually, this step you have to do twice. Pick one variable to be eliminated in 2 of the equations. You have to do that once, and then you have to do it a second time. If that's how it works out, I'll just put in parentheses after it, do twice. But I'm pretty sure that's usually what we're going to have to do. And then once you do it twice, you're going to have 2 equations that you can eliminate. So yeah, we're going to put do twice. The key is when you do it twice, you've got to eliminate the same variable each time. You can't say, all right, this time I'm going to do X and the next time I'll do Y. That won't really help. All right. So when I look at that system, I think there is one letter there that would be pretty easy to eliminate in the other 2 equations by multiplying that equation by a certain number. Does anyone think they know which letter I think would be the easiest to get rid of? Yeah? Chris? Yeah, I think X is going to be pretty easy to get rid of in equation 1 and equation 2. So let's do that. So I'm going to use in this first step equations 1 and 3. When I write a number and circle it, it means it's an equation. So using equations 1 and 3, I'm just going to copy them down. Now, if you're going to copy everything down as you do it, it's going to take up a lot more space. But I think for me, it's the easiest way to do it. 2x plus 3y minus z equals -1. And x plus 4y minus 3z equals -8. Now, Chris said we can eliminate the x's. I agree. What would you multiply the bottom equation by to do that? Yeah? -2. So I'm just going to put a -2. I'm going to distribute. And again, I'm just going to copy the top equation over because I like to see things lined up in columns. So 2x plus 3y minus z equals -1. And now distribute a -2. -2x minus 8y. If I make a mistake, let me know, because it's very, very easy to make a mistake here. Plus 6z equals 16. I think we're good. Great. Now add them up. When I add them, x's are gone. What do I get for my y's? -5y. And my z's? 5z equals 15. Now, something happens here that doesn't always happen, but we can take advantage of it. What could you divide everything in that equation by, and it's still the same equation? You could. You could just make everything a little smaller. -y plus z equals 3. Yeah. Now, if that didn't happen, okay, it's fine. But the fact that it did happen, that's actually going to be easier to work with later on. So I'm going to call this equation 4. I'm going to come back to equation 4 later. But the point is, I now created an equation with just 2 variables. Now I want to do it again. Okay, that's why I wrote do it twice. If you can create another equation with just 2 variables, then we're good. The key though is you eliminated x. You have to eliminate x again, but you can't use equations 1 and 3. What's another pair of equations I could use? 2 and 3. Yep. I mean, you could do 1 and 2, but you're going to be getting into fractions. So let's do 2 and 3. So 2 and 3. I'm going to copy down 2. 3x minus 2y plus 2z equals 15. Again, please let me know if I make a mistake copying. And then 3, we got x plus 4y minus 3z equals negative 8. Which equation am I going to have to multiply, and by what?
The bottom by -3.
Bottom by -3. Okay, so I'll copy the top over. That's unnecessary. Maybe you don't need to do that. But 3x minus 2y plus 2z equals 15. And when I do the bottom, -3x minus 12y plus 9z equals 24. Okay. X's are gone. What about my y's?
-14y.
-14y. My z's?
11z.
11z. And 15 and 24?
39.
39. Okay. And I'm going to call that equation 5. Okay, questions on that? Now I'm going to work with just equations 4 and 5. Forget about 1, 2, and 3. Okay. This problem, just using equations 4 and 5, letter, letter, number, letter, letter, number. It's basically exactly like this kind of problem now. Letter, letter, number. So now we're going to treat it like a 2-variable, 2-equation problem. And we're going to be able to get y, and we're going to be able to get z. Okay. So let's write down 4 and 5. 4 and 5. So 4 is -y plus z equals 3. I think we're supposed to get integer answers, so hopefully we do. And -14y plus 11z equals 39. Okay. Now we want to pick a letter to eliminate here. Do we want to try to get rid of the y or the z? Okay, we're going to get rid of the z. That means you're going to have to multiply the top equation by what?
11.
-11. Yep. So let's copy the bottom. -14y plus 11z equals 39. And the top, we're going to get, well, what do I get in the top?
11.
Yep, 11y -11z, okay? -33. I think we're going to be good. So these are gone. Now we're going to get y. And once you get your first letter, even though we don't even have it yet, we're like 90% done the problem. It's very easy once you get the first letter. Just getting to the first letter. Okay, what do I get for my y's? -3y. And the constant, 6. So what is y? -2. Now that we have y, we can go back to either equation 4 or 5 to get z. I think one of those is easier than the other. 4. Okay. So now, using equation 4, we've got negative y plus z equals 3. Negative y plus z equals 3. Plug that in right there. So what's going to happen when I plug in right there? 2 plus z equals 3. So what's z? 1. So now we've got z, we've got y. Last thing I need is what? X. Now to get x, go all the way back to the original and pick any one you want. First one. Okay. So use the first one. Let's write it down. 2x plus 3y minus z. What was it equal to?
-1.
-1. Okay, so z, it's going to go right there. And y, it's going to go right there. So we've got 2x, forgot what it was, -2, minus z is 1, equals -1. Okay. What's 3 times -2? -6. -6 minus 1 gives me -7. I mean, I'm really showing every step here. You could probably do some of this in your head. 2x is going to equal 6. So x equals 3. Perfect. And I think the one on the test is nice numbers too. So it's a lot to keep track of. I mean, it's a lot, right? But notice once you get that first answer, look at the calculations you have left. It's hardly anything compared to all the stuff you had to do at the beginning. Okay. So any questions on the method? Unfortunately, it's the kind of method that if you make a mistake early on in one spot, it propagates through the whole problem and then it's no good. Alright, so I had another one. I'm not going to go through this one, but one thing I kind of like here is this is missing. So if it's missing, what's actually there?
0.
Right, so that's like a 0y. So I already have an equation with the y eliminated. Maybe I can use that to speed things up somehow. If I can eliminate y somewhere else, then I'm already halfway done the first step. If you didn't notice that, maybe you'd say, okay, I'm going to eliminate the x's here and here using equation 1. So if you multiply it by -2, you could get rid of it here. And if you multiply by -2, you could also get rid of the x's there. Okay. But I would try to take advantage of that somehow. So matrices are what we're going to look at tomorrow. Okay. So other than just telling you it's a more efficient way of solving a problem, I'm not going to show you anything with a matrix today. Nice thing about a matrix is you never have to write any letters. Like if I was doing this problem with a matrix, it would be written like that. All I did was write down the coefficients of everything, and I put a line here so I remember that's where my equal sign was. Okay, so matrices are a lot less writing. And that's what we'll look at tomorrow. Okay, matrices. Okay, so homework tonight. Back in the regular book, not the packet, and it's 1 through 21 on. So I think it's like about 11 or so questions. Okay, remember I'll be after school tomorrow. If there's anything you got to make up from last week. Also, if you have any questions about grades on your report card or anything, just come see me and we can take a look at that too.